Right, so in the last video, we defined what energy signals and power signals were. In this video, let's actually go ahead and work through this example computation. We'll do a few different examples, actually. We'll do both some energy computations and some power computations for some very specific signals. So let's go ahead and get started. So energy and power computations, part A, let's start off with a very simple signal. Let's let x of k equal an impulse. So a discrete time impulse is 0 everywhere, and at time k equals 0, it's equal to 1. So here's a plot of the discrete time unit impulse. It's 0 everywhere, except for at this time it has a single value of 1. And we're going to go ahead and compute the energy of this signal. This equation right here is the equation for E that we introduced in the previous video. And it says to compute the energy of a signal, we take the magnitude squared of the signal and then add up all those values for all time. For this particular signal, that's pretty easy because most of the values of the signal are 0. So the magnitude of 0 is 0, magnitude of 0 squared is 0. So there's going to be a lot of zeros in this sum. The only time we won't have a 0 is right here at time k equals 0, where we'll have the magnitude of 1, which is 1 squared, and 1 squared is also 1. So you can actually just write this summation out. It's pretty easy. It's 0 squared plus 0 squared plus 0 squared, dot, 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 for forever. There's a single 1 squared in the sum, followed by an infinite number of 0 squareds. And obviously that's equal to 1. So the energy of the discrete time unit impulse function, delta of k, is 1. Since this number, E, that we just computed is bigger than 0 and less than infinity, 1 satisfies that inequality there, we can declare that this is indeed an energy signal. So the discrete time unit impulse signal is an energy signal. All right, let's do something a little more complicated. Let's work with this signal right here. X of k is equal to alpha to the k for k greater than or equal to 0, and it's equal to 0 for all other times. So for all the negative times, it's equal to 0. And we're going to assume here that alpha is just some real valued number whose magnitude is less than 1. So it's 0.8 or 0.2 or something like that. So if I had to make kind of a cartoon sketch of this, x of k might look like this. It's obviously 0 here at negative time. Alpha to the 0 is 1, so at time k equals 0, the signal is equal to 1. Then at time k equals 1, alpha to the 1 is just alpha. So we have alpha, then alpha squared, then alpha cubed, and we get this kind of decaying exponential sequence of numbers. We're going to compute the energy. All right, so let's compute the energy. Another representation of this signal that'll be useful is this equation right here. You can see what we've done. We've kind of taken this piecewise defined signal and written it as a simply defined signal by using the unit step function. Remember, U is the unit step function. So let's go ahead and compute E. We'll start off just by writing down the definition again. It's the magnitude squared of the signal summed over all time. So here's our starting equation. Obviously, all of these values back here are 0, so we don't even need to include those in the sum. So as a first step, you can see what I did. I changed my lower limit to just start counting at k equals 0, because I've just thrown out all these 0 terms, which contribute nothing to this overall summation. All right. For values of k equals 0 to infinity, we actually know what x of k is equal to. It's actually equal to alpha to the k. So I can just replace x of k with alpha to the k because we are working only with values for k greater than or equal to 0. All right, so that leads to that equation right there. And then we can just do a little bit of algebra. It doesn't matter which order you do the raising. Alpha to the k to the 2 is the same thing as alpha to the 2 to the k. There's properties of exponents. And the reason we like it written like this is because this is a very special form. This is a sum from k equals 0 to infinity of some number raised to the k. That's a very special summation called a geometric series. If you're familiar with that, you might be able to write down this answer right away. I usually have to go look things up again. And if you go look things up, Google something, you'll see this equation right here. Anytime that we sum from k equals 0 to infinity of some number raised to the k, the answer for that summation is 1 over 1 minus r, as long as the magnitude of r is less than 1. Well, that's exactly the case that we have right now. We knew that alpha was less than 1, so alpha squared is definitely less than 1. So we can use the equation in green to replace this sum very easily. It's going to be equal to 1 over 1 minus whatever number is being raised to the power k. In our case, the number r is alpha squared, and hence it's 1 over 1 minus alpha squared. So that is the answer. That is the energy of this signal. Again, this is just a number, right? 1 over 1 minus alpha squared, some scalar. It's a number bigger than 0. It's a number less than infinity. So this signal that we just worked with is indeed an energy signal. All right, one more. Let's do a power signal computation. So let's work with the signal x of k that is 1 for all values of k greater than or equal to 0, and 0 for all other values of k. So this is basically just the unit step, right? So if I plotted this signal, it would look like this. It's 0 for all negative time, and then at time 0 it turns on to a value of 1, and it stays 1 for forever. Hopefully you can just look at this right here and realize that if we computed the energy would be infinity, right? We'd end up adding up 1 squared an infinite number of times. So hopefully you can just look at this and say, wow, that is not an energy signal, because if I computed E, I would get infinity. So if we're going to compute something that's a little bit more interesting, power is going to be the interesting quantity for this signal. So let's compute the power for this signal. This equation I circled there in red is the equation that we wrote down in the previous video. It's how we defined P. It's the limit as n goes to infinity of 1 over 2n plus 1. And then a very similar thing here. It's still a magnitude squared summed. It's just summed from minus n to n. All right, so let's work on that equation just a little bit. So I didn't do anything here in the front in terms of the limit, but I replaced k equals 0 as the lower limit because, again, I don't need to add in all these zeros back here. They don't change the summation at all. Once I've limited myself to working on just the interval k equals 0 to capital N, I know exactly what x of k is equal to on that time interval. It's equal to 1. So I replaced x of k with 1. So I have 1 squared, which is also 1. So not too difficult of a summation to do. All we have to do is ask ourselves, what is this equal to? So I've got 1 squared plus 1 squared plus 1 squared, which is 1 plus 1 plus 1. And I keep doing that for all values of k equals 0, 1, 2, 3, 4, 5, up to capital N. So basically I'm just adding up 1 a whole bunch of times. How many times? Well, it's the top limit minus the bottom limit plus 1. So capital N minus 0 plus 1 is n plus 1. So that summation has n plus 1 ones in it. So I can go ahead and write that down right here. That summation is actually equal to n plus 1. So let's rewrite this a little nicer. The limit as n goes to infinity of the ratio n plus 1 over 2n plus 1. If you remember your basic calculus, what we need to do is kind of look at the ratio of the largest power of n, and that ratio is 1/2. So the power of this signal, the power of the unit step signal, is 1/2. Since that number we just computed is bigger than 0 and less than infinity, this is indeed a power signal. All right, that wraps up this video. We computed the energy for 2 signals. We computed the power for a signal. And obviously, it's easy to come up with lots and lots of other examples. But the general strategy is always write down the equation for E or P and then carefully substitute in the signal you're given, simplifying the bounds of the summation using basic algebra. You often need to work it into some type of summation that you know the answer to. In this case here, it was an easy summation because we were just adding up 1 over and over and over again. Sometimes you run into geometric series. Sometimes you run into other forms that you can kind of Google and look things up in a table, but that's the general strategy.